Hey guys, welcome to lesson 8.1 on reciprocal functions. Now today we're going to talk about kind of a new way to classify relations. And that classification is going to be what type of variation the relation has. So we're going to introduce the idea of variation today, and there's a few different types of variation that we're going to discuss. The first kind of variation that your function might have is what's called inverse variation. And inverse variation is a relation that's represented by one of the equations in these forms. Xy is equal to k, y equals k over x, or x equals k over y. Now notice how all three of these equations are really the same equation. They're just in different forms. We've isolated all three of the variables separately. Now the main form of this equation that I want you to look at is the one in which y is isolated. So when we're referring to an inverse variation, we are referring to any relation whose equation is represented like so. Y equals some constant divided by our inputs, and that is providing us with our outputs, y. So basically, if you have any sort of relation where you're taking a constant, dividing it by your input, and that's providing you with your output, you are looking at an inverse variation. Now, the second type of variation that we're going to look at is kind of the opposite. So we're going to talk about joint variations. Now, just a quick heads up, another way to express joint variations is by saying direct variations. So direct variations and inverse variations are two kind of interchangeable terms that you might run into. So just be aware of that. So a joint or direct variation is basically a relation in which one variable varies directly with respect to each of two or more variables. So for example, we might have the equations, this should be a z right here, so make sure you cover that up with a z. An example of this type of variation might be these equations. Z equals 8 times xy, or t equals k times pv. In both of these cases, notice how we have some constant that's being multiplied to the two variables that represent the inputs. So here we have a constant of 8 being multiplied by the two variables, and then down here for the t equation, we have some constant k being multiplied by the two variables. So basically, any sort of relation where we have some constant being multiplied by our inputs, or in other words, some linear relationship, then we are looking at a joint or direct variation. Now, the formulas that we're going to use to represent direct variations today are going to be the formulas y equals k times x, where again, k is some constant and x is the inputs, or the equivalent form, or one of the equivalent forms of this equation, which would be k equals y over x. So these are just basically two different ways to represent the same equation, but this is what the equation is going to look like for the relation. This is the formula we would use to figure out what the constant is of that relation. Okay, and the third type of variation that we're going to talk about today is combined variation. And what this is basically any relation in which one variable varies with respect to each of two or more variables. Now, there are a few different types of combined variation that you might see today, and we're going to go through each of them separately. So the first type of combined variation you might see is one where we have some variable, which we'll say z here, some variable z that varies jointly with two other variables, x and y. If you see this sort of situation, the equation that we're going to use to represent this variation is z equals our constant k multiplied by two of the inputs, x and y. Notice how we kind of said this above here, right? We talked about joint variation, and joint variation is where we have that constant being multiplied by the other variables. So same thing down here. If z varies jointly with x and y, we have a constant k being multiplied by the variables x and y. Now, another type of variation that we might see is z varies jointly with x and y and inversely with w. Well, if we're varying jointly, remember we have some constant multiplied by the variables. So if z varies jointly with x and y, we have some constant k being multiplied by the variables x and y. And if we're varying inversely with w, that means that we are essentially dividing by w. Okay, so that's how we're going to represent this type of variation in an equation's form. So just connect the vocabulary with what's happening in the equation. And then last but not least, we have z varies directly with x and inversely with the product wy. Well, again, if z varies directly, that means we're multiplying some constant by whatever that variable is. So z varies directly, which means we have some variable k multiplied by x because we are directly varying with x. And we're varying inversely with the product wy. So again, if we're varying inversely, we're going to write whatever that is in the denominator. So if we're varying inversely with the product wy is in the denominator. So we have z equals kx over wy. All right, so those are just a few types of variations we might see as we're going through our examples today. Now let's move down to our first example, where we're going to talk about how to identify direct and inverse variations. So example number 1, is the relationship between the variables a direct variation, an inverse variation, or neither? Write the function that models these either direct or inverse variations. Okay, so let's look at part A. We have a table of a ton of x and y values, and we need to determine what kind of variation this is. Now, I just want to illustrate to you what a direct variation looks like and what an inverse variation looks like. So I'm going to tell you right now that A represents a direct variation. Now, when we were talking about direct variations, we said that direct variations are represented by the formula y equals some constant that is being multiplied to our inputs. And this is also a joint variation, right? Because we said direct and joint are interchangeable. Another way that we could write this equation is we could isolate for k, and then we have the equation k equals y over x. And this is useful because really what we want to do when we're determining if something is a direct or inverse variation, we want to figure out what k is equal to. Okay, so notice how we have a ton of values for x and y, but we don't necessarily know what k, our constant, is. So our goal is to figure out what the constant is, and most of all, we want to make sure the constant is consistent with each x and y ordered pair. So what we're going to do is we're going to figure out what k is equal to for each of these ordered pairs. And if k is constant for all of the ordered pairs, that means that we are in fact looking at a direct variation. So I have k equals y over x. For my first ordered pair, I have 0.2 comma 8. So y is 8, x is 0.2. Our constant k is going to have to be 8 over 0.2. Let's look at the second ordered pair. We have 0.5 comma 20. Y is 20, x is 0.5. So if you plug this into the formula, k equals y over x, this is going to be what k is equal to. For the third ordered pair, we have 1 comma 40. So plugging that into the formula, we'd have 40 over 1. And for the last ordered pair, 1.5 comma 60, we would have 60 over 1.5. Now again, in order for this to be a direct variation, k is going to have to be the same number for all of the ordered pairs. So let's go ahead and figure out what it is. Well, I know if I use my calculator, 8 divided by 0.2, 8 divided by 0.2 is going to give me 40. If I plug 20 divided by 0.5 into my calculator, I'm also going to get 40. 40 divided by 1 is 40. And if we plug 60 divided by 1.5 into our calculator, we do in fact get 40. So notice how all of these values for x and y that we plugged into the formula k equals y over x, they all gave us the same value for k. So therefore, yes, since we found that k is consistent for this formula, since this formula represents direct variation, we are looking at a direct variation. So I'm going to say yes, it is in fact a direct variation. Now, if I need to find the model for this direct variation, I'm going to use the original formula y equals kx. Since I know that k is clearly equal to 40, all I'm going to do to find the model is I'm going to plug 40 in for k in that formula. So we're going to have the model y equals 40 times x. And this is the model of the direct variation that we have above. All right, you guys, very good. And again, we are looking at a direct variation because we satisfied this equation up here. Okay, now let's look at an inverse variation. So I'm going to tell you right now that part B is an inverse variation. Now, like we said before, and I kind of expressed this above when I was talking about what an inverse variation is. Remember, an inverse variation is where we have some constant that we're dividing by our inputs. So as our inputs are getting greater, since we're dividing by a larger number as those inputs get greater, theoretically, our y values should be getting smaller, where with direct variation, it's the exact opposite. We have some constant that we're multiplying by our x's, so as our x values get bigger, so should our constants. So we noticed right off the bat that this table kind of represents what an inverse function would look like, or an inverse variation. And we know that inverse variations follow the formula y equals some constant k divided by our inputs x, okay? And we could rewrite this equation by isolating for k, and we would get k equals y times x. So it's kind of like the polar opposite of the direct variations. All right, so basically, in order for this table to be an inverse variation, we have to satisfy this equation and this equation, okay? So what we can do is kind of the same thing we did before. We're gonna figure out what our constant is equal to for each of the sets of ordered pairs. And if our constant is the same for all of the ordered pairs, that means that this does in fact represent an inverse variation because it satisfies the inverse variation formula. Okay, so let's figure out what k is equal to for my first ordered pair. So if k is equal to y times x, k is gonna have to be equal to 0.2 times 40. So 0.2 times 40 is the first thing I'm plugging in. And that also has to be equal to 0.5 times 16. Again, k has to be the same for all of my ordered pairs. That also has to be equal to 1 times 8.0, or 1 times 8, which also has to be equal to 2 times 4. Okay, so let's go ahead and plug all of those in. So my first situation, I have 0.2 times 40. If I plug 0.2 times 40 in, I'm going to get out 8. Then I have 0.5 times 16. Plug that into your calculator, you're going to get 8. 1 times 8, you get 8. 2 times 4, you get 8. So since our constant is the same for all of the ordered pairs, k is clearly going to equal 8, and it satisfies the inverse variation formula. Okay, so if I need to write the model or the equation for this table of values, what I'm going to do is I'm going to plug in 8 for my k value, giving me y equals 8 over x. So the formula or the equation that we're using is y equals 8 over x. All right, next example. Let's look at part C. Now, this is the last table that we're going to look at and determine if we're looking at a direct or inverse variation. So now we're going to go ahead and determine it by going through the process of elimination and looking to see which one, if any, it satisfies. So let's go ahead and look and see if this is a direct variation first. So if this is a direct variation, we need to satisfy the equation y equals some constant times x, or if we solve for k, we're going to get k equals y over x. So our constant k is going to have to be consistent for all of these ordered pairs in order for this to be a direct variation. So let's go ahead and explore. We have k equals y divided by x. Let's plug in my first ordered pair. I have 40 for y, 0.5 for x. That has to be equal to 12 for y divided by 1.2 for x, which also has to be equal to 10 divided by 2.0, or 2, which also has to be equal to 6 divided by 2.5. Okay, so if I plugged this in to my calculator, I would find that 40 divided by 0.5, that's going to give me 40 divided by 0.5, that's going to give me 80. Then if I say 12 divided by 1.2, that's going to give me 10. We can already see where this is going. 10 divided by 2, that gives me 5. And 6 divided by 2.5, that's going to give you 2.4. So as we can see, these k values are not consistent, so this is not going to be a direct variation. So I'm going to say this fails the test for the direct variation. Now let's look at inverse variation. So in order for a relation to have an inverse variation, we need to satisfy the equation y equals some constant divided by our inputs x. If we were to solve for k here, we would have the equation k equals y times x. Okay, so if I plug in all of my x and y values to this equation for k, all of my k values should be consistent. So I have k equals y times x, which here is 40 times 0.5. So I have 40 times 0.5. That has to equal 12 times 1.2, which has to equal 10 times 2.0, which also has to equal 2.5 times 6, or 6 times 2.5. Okay, so let's go ahead and plug those into our calculator. Well, 40 times 0.5, that's going to give me 40 times 1/2, which is 20, which has to equal 12 times 1.2. 12 times 1.2 is going to give me 14.4. Okay, then we also have 10 times 2, which gives us 20. And 6 times 2.5, 6 times 2.5 is going to give you 15. So as you can see, these numbers are not all equal to each other. So this is not an inverse variation either. It fails the inverse variation tests. Okay, so for this reason, since it fails both direct variation and inverse variation, unfortunately, this relation is neither a direct variation or an inverse variation because it fails when plugging in to both of the formulas for k. Okay, next example. Example number 2. Now we're going to determine an inverse variation. Suppose that x and y varies inversely and x is equal to 2 and when y is equal to -3. Part A asks what function models the inverse variation. Well, first of all, we know that we're talking about an inverse variation because the problem tells us x and y vary inversely. So right off the bat, we already know what formula we're going to use. We know that inverse variations are the situation. We have the equation of the form y equals some constant k divided by our inputs x. If we have a relation that represents this equation, we are looking at an inverse variation. And we could also rewrite this equation to get k by itself by saying, okay, k equals x times y. And this is just an easy formula to use if we need to figure out what the constant k is equal to. Okay, so if we know that x is 2 and y is -3 and we need to write the model for the inverse variation, well, obviously I got to figure out what is k equal to. Because obviously in order to write the model, I got to figure out what that k value is. So we know we can find our constant k of an inverse variation by plugging in 2 and -3 into the equation k equals x times y. So k is going to have to equal x times y, which is 2 times -3, giving us k equals -6. So since k equals -6, if I plug that into this formula here, I can see that the equation or the model of this inverse variation is going to be y equals -6 divided by x. All right. So now we need to figure out what the graph of the equation y equals -6 over x is equal to. Well, first of all, let's talk about the domain of this graph. The domain is going to be all real numbers, but we can see very easily that 0 is not an acceptable x value because that would give us an undefined function. So our domain is going to include all real numbers except for x. So that means there's going to be an asymptote at the line x equals 0. Okay, now let's think about the outputs or the range of this function. Well, since we have not a positive number, we have a negative number in the numerator, but basically we have a non-zero number in the numerator, and obviously x cannot be equal to 0. So there is no situation where we will divide -6 by some number and it will give us an output of 0. So for that reason, also, another asymptote is going to be the line y equals 0, because 0 can never be an output of the function. So now, using those two facts, what we're going to do is we're going to create a table of values, and I'm going to plug in some negative numbers and some positive numbers to see what we get. So let's plug in -4, -3, -2, and -1, and we can also plug in some positives 1, 2, 3, and 4. Okay, so if I plug in... Actually, let's go ahead and even narrow this down a little bit. I don't need to plug in -4 or +4 because that's just going to give me some ugly numbers right here. But -6 divided by -3, that's going to give me +2. So -3, +2, I'm going to plot that point. Then -2, plug that into this function. We have negative 6 divided by negative 2. That gives me positive 3. So at negative 2, I go up positive 3. Oops. Positive 3 right here. And then negative 1, well, negative 6 divided by negative 1 is positive 6. So at negative 1, I'm going to go up 6 on my graph. As we can see, we have asymptotes here on the x and y axes. So this line or this curve is going to come really close to touching those asymptotes, but we're never going to quite touch. We're going to come extremely close, but we're never going to quite touch. Okay, now let's plug in the positive values. I have 1, so negative 6 divided by 1, that's going to give me negative 6. So 1, negative 6 is a point right here. Then at 2, negative 6 divided by 2 gives me negative 3. So at 2, negative 3, I'm going to have a point right here. And then at 3, negative 6 divided by 3 gives me negative 2. Okay, so at 3, I'm going to go down 2. And I can see that, again, this curve is going to approach the axes, but it's not going to quite touch the axes. So this is the graph of the function y equals negative 6 over x. Last but not least, part C, what is y when x is equal to negative 5? Well, we already know that the formula here, or the equation of this model is y equals negative 6 over x. So if we use that formula, y equals negative 6 over x, all I have to do to figure out what y is equal to when x is negative 5 is I'm going to plug in negative 5 for x. So y equals negative 6 over negative 5, and that's going to give me y equals positive 6 over 5. So we have the ordered pair when x is negative 5, y is 6 over 5. And let's see if that's true. Well, yep, that looks about true, because right here at the x-coordinate negative 5, we can see that our graph is right about there at 6 over 5. So that makes total sense. This is the answer. All right, you guys, moving on to the next page. Okay, so now we're going to look at a real-world situation that models an inverse variation. So example number 3, a recent hurricane left debris around the neighborhoods near your school. The table below shows the time t in minutes that it takes a group of n students to remove the debris from an average size yard. So what we're looking at here is we're looking at a relation. We have our inputs represented by n and our outputs represented by t. Now we know that if we're looking at a relation, we can determine whether or not the relation is a direct or an inverse variation. And if we find that it's one of those variations, then we can easily write a formula to represent that relation. So we know that direct variations have the formula y equals k times x. So typically with direct variations, as the inputs are getting greater, the outputs are also going to get greater because we're multiplying bigger numbers to that constant. But if we're looking at an inverse variation, those have the formula y equals some constant k over x. So with inverse variations, as the input gets greater, then the output is going to get smaller because we're taking this constant and we're dividing it by bigger and bigger numbers. So as the x values or as the inputs get greater, the output is going to get smaller. So looking at this table, notice how the outputs are getting smaller as the inputs are getting bigger. So what that means is we're probably looking at an inverse variation, and we know that the formula for an inverse variation is y equals some constant k over the inputs x. Now, if we look at part A, it says, what function models the time needed to clear the debris from an average size yard relative to the number of students who do the work? So essentially what we're doing is we're creating an equation that will represent this table of values. So what we're going to have to do is we're going to have to use the fact that we have our ordered pairs n comma t instead of x comma y, and we can plug those in to figure out what the constant's going to be, and then we could easily write an equation. Now, obviously, I'm looking at different variables here. Instead of x, I have n, and instead of y, I have t. So I'm going to replace this formula with t equals k over n, okay? Again, that's because y is t. In this case, my outputs are t, and my inputs, which are usually x, are n in this case. And then I could also easily write a formula for the constant by multiplying both sides by n, giving me k equals n times t. Okay, so now what I'm going to do is I'm going to figure out what the constant is based on this table. So I'm going to use the first ordered pair, n is 1, and T is 225. So if I plug those into that formula, I'm going to use this formula because I want to get K by itself. So I'm going to have my constant is equal to my N value, which is 1. So I'm going to plug in a 1. And that's multiplied to T, which in this case is 225. So I'm multiplying 1 times 225. Now, obviously, that's going to give me K equals 225. So my constant for this situation is 225. Now, you could always verify that this is actually an inverse variation by plugging in all of your ordered pairs and seeing if your constant is 225. But like I said, I'm telling you right now, this is an inverse variation. So if we were to plug this K value into the original, we're actually going to use this one with the T and N. What we're going to get is T equals, instead of K, I have 225 over N. And this is the model of the relation that we see above. Okay, so part B says, how many students should be there to clear the debris from an average size yard in at most 25 minutes? So what we're trying to find is, okay, what is the N value going to equal? So how many students should be there if I want to finish the job in 25 minutes? We know that minutes, or the amount of time it takes to clear the debris, is represented by T. So in this case, what I know is T equals 25. So I'm going to use this formula that I just created, T equals 225 over N, and I'm going to solve for N because I want to know the number of students. So we're going to have, instead of T, I'm going to put 25 is equal to 225 over N. So again, I want to solve for N. So what I'm going to do is I'm going to multiply both sides by N to get it out of the denominator. So now we get, these N's are going to cancel each other out. We get 25N is equal to 225. Divide both sides by 25. And we are going to find that the number of students needed to clear up this debris in 25 minutes is 225 divided by 25, which is 9 students. Okay, so I need 9 students if I want to get this job done in 25 minutes. All right, and that is how we use the inverse variation for a real-world situation. Let's go ahead and move on to the next example. Okay, so we're going to look at another real-world example, but this real-world example is going to use the combined variation, which you might recall is the third type of variation that we talked about in the beginning of this lesson. So example number 4, the number of bags of mulch you need to cover a planting area varies jointly with the area to be mulched, which is represented by A in square feet, and the depth of the mulch, D, in feet. And again, we are also talking about the number of bags of mulch you need to cover this area. If you need 10 bags to mulch 120 feet square to a depth of 3 inches, how many bags do you need to mulch 200 feet squared to a depth of 4 inches? Okay, well, let's go ahead and first of all, talk about what the process is for solving this problem. So obviously, there's a lot of moving parts to this question, so I'm going to walk you through it. The first thing we should always do, no matter what word problem we're solving, we need to make sure we define our variables. So my first step is going to be to define my variables. And like I said, this works in a number of different math classes. Always, the first thing you should do is make sure those variables have meaning to them. So we're talking about 3 things, right? First of all, we're talking about the area of some planting area, right? The area that needs to be mulched, and that is in squared feet. So I'm going to say A represents the area to be mulched, and the units that I'm using are feet squared or square feet. Okay, the second thing we're talking about is we're talking about the depth of the mulch, D, in feet. So I'm going to say D represents the depth, okay, the depth of mulch, and the unit for this depth of mulch is going to be feet. So that is what D represents. And then last but not least, we're also talking about the number of bags. So since we need to know something about the number of bags, we should assign a variable to it. So I'm going to say B equals the bags of mulch. So once I assign my variables, then I can move on with actually setting stuff up. Now, you might have noticed when we were reading this problem, I had 2 different units happening at the same time. I have feet, which are what my variables are represented as, but then I also have some measurements that are in inches. So since my variables are represented by feet and square feet, I'm going to want to convert these inches into feet. So the second step is to convert the inches to feet. Okay, so now let's go ahead and convert both of those inch measurements to feet. So 3 inches. Well, we know that there are 12 inches in 1 foot. So to figure out how many feet 3 inches represents, we're going to divide 3 inches by 1 foot, which is 12 inches. And this is going to give you, if you simplify that fraction, 1/4 of a foot. Okay? So 3 inches is 1/4 of a foot. Now let's do the same thing to the 4-inch measurement. Well, I know that 4 inches, if I want to convert that to feet, I'm going to have to divide it by 1 foot, which is 12 inches. If I simplify this fraction, that's going to give me 1/3 of a foot. So these are the measurements of those inches in feet. So now, the third step, after we've got all of our stuff set up, we're going to want to write some sort of equation, because in order to solve this problem, not only am I going to have to set up an equation, but I'm going to have to solve it. So let's go ahead and take a look at what formula we're going to use. Well, obviously, we are talking about a combined variation. And what the problem said is that the number of bags B varies jointly with the area to be mulched A and the depth of the mulch D. So if you recall from the first page, if we are varying jointly with 2 variables, well, in our case, B is varying jointly with the 2 variables that we talked about, A and D, that means we're going to use this formula. Z equals some constant times the 2 variables that we are varying jointly with. So I'm going to set up an equation that says, all right, well, B varies jointly, so B is going to vary jointly, which means we're multiplying some constant K to the 2 measurements that we have, which are A, the area to be mulched, so K times A, and D, the depth of the mulch. Okay, so this is going to be the formula I have to use. Now, obviously, I've already figured out what some of these are equal to, and we have a couple of different scenarios listed up here. I have my one scenario that says, okay, 10 bags are needed to mulch 120 feet squared. Square feet, again, is area, so the area here would be 120. B would be 10, and I know that that's going to give me a depth of 3 inches, okay? So D is going to be 3. So the first scenario, I can easily plug those 3 things in to the variables to figure out what the constant is. Well, if I'm finding the constant, I could also use this formula, K equals B over A times D. So let's go ahead and plug it all in. Well, I know B is equal to 10 here, so I'm going to say K equals 10 over A times D. Well, the area is 120, and the depth is 3 inches, which I said 3 inches converted over to 1/4 of a foot. So I'm going to say in the bottom, A times D is 120 times, that's going to be 1/4. Okay? So then if I multiply 120 by 1/4, that's going to give me 10/30. And then if I'm dividing 10/30, that's going to give me 1/3. So K equals 1/3. So the formula I'm going to use is, well, I'm just going to use this formula up here, but plug in K. So I have B equals, instead of K, I'm going to put, that's 1/3 times A D. And this is the formula I'm going to use. So then for part 4, this is asking the final question, how many bags do you need to mulch 200 feet squared? So A is going to be 200 feet squared, and a depth of 4 inches. So D is going to equal 1/3 of a foot. So I'm just going to plug that in to figure out how many bags I need. So I should have, the last step is to solve the problem. So I should have B is equal to 1/3. Again, if we're looking for the bag, how many bags we need with 200 feet squared, A is going to be 200. So I have 1/3 times 200 times D. Okay, again, we're looking at a depth of 4 inches, which is 1/3 of a foot. So I'm plugging in 1/3. And this is going to be what I am calculating. Now, obviously, 1/3 times 1/3 is going to give me 1/9 times 200. And if I plug that into my calculator, I know this is a little sloppy, but that's going to equal 22.2. So what this means is, if we were to round the number of bags that we need in order to mulch that depth, we are going to need, well, since we have a little bit more than 22, I'm just going to say, just to be safe, we need 23 bags. So I'm just going to say we need 23 bags. Okay, so that is the final answer to this question. All right, let's go ahead and move on to the next page. So a couple more examples to finish this off. Number 5, find the constant of variation for each variation, then write an equation that can be used to solve the missing value. Part A, if z varies jointly with x and y, when x is 3, y is 5, and z is 120. Find x if z is 35 and y is 7. So what we're going to have to do is we're going to have to set up an equation figuring out, okay, well, what are we actually doing here? What formula are we using? We're going to have to find the constant of variation, so find what k is equal to. Then after we write a model for the situation, we're going to figure out what the missing value is. So first of all, let's go ahead and take a look at what we have. Z varies jointly with x and y. Well, if z varies jointly, what that means is z is equal to some constant k multiplied to the other variables x and y. We could easily rewrite this equation a little bit by isolating k. All we have to do is divide both sides by x, y. So we could easily calculate our constant by saying k equals z over x, y. All right, so I know my scenario here is x is 3, y is 5, and z is 120. This is my first scenario, so I can figure out what the constant is by plugging those 3 in to the equation. So instead of k equals z over xy, I'm going to have k equals, I'm going to plug in z is 120, so 120 over xy, which instead of xy, I'm going to put 2 that's x is 3, so I'm going to put 3 times y is 5. So that's going to give me 120 over 15. And if I divide 120 and 15, I'm going to see that k is equal to 8. So I'm going to say k equals 8. Now, if I know that k is 8, I could easily plug k into this formula, and that would give me a formula to use to find x in this scenario. So we could say, well, instead of z equals kxy, I could say z equals 8xy. And I'm just going to say right here, this is the constant. I'm going to put a purple 8. This is the constant that I found right here. Okay, so now I need to find x if z is 35 and y is 7. So what I could do is I could plug in z equals 35, y equals 7, and I could figure out what the missing value x is. So instead of z, I'm going to put 35 equals 8 times xy, but instead of x, well, I'm actually going to keep that x because I got to solve for x, but instead of y, I'm going to put 7. So I put x times 7. Okay, so now I can obviously simplify this a little bit. I get 35 equals, we know that multiplication is commutative, so 8 times 7, well, 8 times 6 gives me 48. So 8 times 7 is going to give me 56. So I have 56 times x. And then if I want to get x by itself, all I have to do is divide both sides by 56. So take both sides here. Oops, super messy here. Divide both sides by 56. We're going to get 35 divided by 56, that can simplify to 5 over 8. So I'm going to get x equals 5 over 8. All right? So this is a very common question that you might run into. Part B, if y varies inversely with the square of x, when x is 3, y is 7 over 15, find y if x equals 5. Well, obviously, we know if we're talking about an inverse variation situation, we're going to have y equals some constant over whatever is being varied inversely. So what's being varied inversely here is the square of x. The square of x is just x squared. So if we're varying inversely with the square of x, this is going to be y equals k over x squared. Now we could easily rewrite this equation and say k is equal to y times x squared, or x squared times y. And then we could figure out what k is equal to by plugging into the formula. So I need to figure out, well, if x is 3 when y is 7 over 15, what's my constant? So I'm going to say k has to equal So I'm going up here. K has to equal x squared, which in our case would be 3 squared, times y, which is 7 over 15. That's going to give me K equals 9 times 7 over 15. And then obviously 9 and 15 are both divisible by 3. 9 divided by 3 is 3. 15 divided by 3 is 5. So 3 times 7 on the top is going to give me K equals 21 over the denominator, which is 5. So K is 21 over 5. Now, all I have to do is I have to plug that into the formula. If I know K is 21 over 5, I'm going to plug K in right here. So I get Y equals 21 over 5 x squared. And if I'm plugging in, well, I need to find y when x is 5. I'm going to plug 5 in for x here. So I have y equals 21 over 5 times, that's going to be 5 plugged in for x squared. That gives me 21 over 5 times 25, which is going to give me 21 over 125, and this is my final answer. I cannot simplify that anymore, so I'm going to leave it like that. All right. And that is how you do number 5. Last example. Example number 5 says, gravitational potential energy, PE, is a measure of energy. PE varies directly with an object's mass m and its height h in meters above the ground. Physicists use g to represent the constant of variation, which is gravity, giving us the formula PE equals gmh. Once again, our variables are already defined for us. We have an object's mass m, height h in meters above the ground, and g represents the constant of variation, which is gravity. Now, the next step of direction says use the gravitational constant of 9.8 meters squared and joules for PE. Well, what this is saying here is for the gravitational constant, which we refer to as g, which is the constant of variation, we're using 9.8. So I'm going to say g is equal to 9.8. So example 5 says, how much potential energy would a 41 kilogram diver have standing on a 10 meter diving platform? Okay, so we obviously have a few different variables that are already defined for us. I can say that g is equal to 9.8, which we expressed above. We also see that our mass here, which is m in the formula, is 41 kilograms. So I'm going to say m is equal to 41. And then h is the height above the ground, which is 10 meters, because we're jumping off of a 10-meter platform here. So our height, h, is going to equal 10. Okay, so we're going to plug it into the formula. PE equals gmh. So in our case, PE is going to equal g, which is 9.8 meters per second, times m, which in our case is 41 kilograms, times our h value, which is our height, which in our case happens to be 10 meters. So what this is if we put this in our calculator, we're going to get PE equals, multiply all those together, we'd get 4,018. And again, the units here are meters squared times kilograms over s, all right? Because that's the units that we have for joules. So instead of writing all that, I'm just going to say, hey, my potential energy is equal to 4,018 joules. Okay? So this is my final answer. Plug it into the formula, and you get the answer, 4,018 joules. All right, guys, nice work today. Go ahead and log into Alex and finish your assignment, and I will see you back here next time. Thank you.